So the inverse trig functions were the last set or family of functions that we wanted to be able to talk about. So we're done with looking at all the different types of functions. And starting next week, we'll be able to do calculus on all of those functions, or try to, and eventually succeed. For now, we just have one property of functions that's important that doesn't need any calculus. So we'll talk about it right now. It's called continuity. So there's three ways that a graph can fail to be continuous. There's this thing, which is called a removable discontinuity, because if I just put this one point back here, the graph would be continuous. The informal definition of continuous, I should say, is that you can draw the graph without lifting your pencil off the paper or your chalk off the board. So here, if I'm trying to draw this, I need to lift the chalk off the board to draw this point and then come back. So we're discontinuous there. We're discontinuous here at this vertical asymptote because I need to jump over to get to the other side of the asymptote, whether this were coming down or coming up like that. So this is another place that we can be discontinuous. Some people call this an essential discontinuity as opposed to removable. And then there's this one where I'm going along here and then I jump down to here. And this is called a jump discontinuity. The names aren't important. What's important is the definition of what it formally means to be continuous and informally. Informally, again, you're continuous if you can draw the graph without lifting your pencil off the paper. So this graph here was discontinuous at x equals 1, x equals 2, and x equals 3. So let's figure out what caused that to happen. And to do this, we're going to use our favorite notion from the past couple weeks of limit, which we're going to see a lot of next week. In this case, as x approached 1, we were approaching the same y value from each side. So this limit as x approaches 1 of f of x actually exists. It's whatever this y value is, say 5. The trouble is that the limit is not the same as the actual y value at the point. So that's why we were discontinuous there. Here, the limit doesn't exist, right? We get a different value from the left and the right. And the function itself doesn't exist at this point because I don't have any filled in point here. So there's no filled in point. So the limit doesn't exist and the function doesn't exist. But we don't say that if two things don't exist that they're equal, because you can imagine unicorns don't exist, the Easter Bunny doesn't exist, and yet unicorns and Easter Bunny are not equal to each other. Finally here, the function is defined is whatever this y value is, but the limit doesn't exist because I get a different limit from the left than from the right. So in order to rule out all three of those things happening, what we can say is that f is continuous at a point x equals a if the limit as x approaches a of f of x is the same as the y value at that point. In other words, if I matched up this, if I shifted it up there and the y values matched, or if I slid this point down into there and made the y values match. So what should I write here? How do we denote the y value at x equals a? We simply write f of a. And then you can check for yourself that if this limit equals that, then that avoids all three of those problems with discontinuity that we had there. So congratulations on making it through the first 2 weeks or modules. We've done all of the pre-calculus prep work that we need to do. And next week, we will start the exciting world of calculus.